which is Newton's method. And this is a method for finding zeros. That's what it's for. And let me just try to explain the underlying idea. So here's the idea. So you have a function, and let's say that you have a function like this, and it goes through the it intersects the x-axis right here. Okay, that's the x-axis, and maybe here too. Okay, and maybe some other places, but who knows? Okay, we'll just look at those two places. Okay, so the idea of Newton's method is what you want to do is you first of all choose a point that you want to find out what this point what this value is. That's the idea. So you choose a value that maybe is close to that, and you call that value your x1, your initial value. Okay, so like they're doing it right here where they're choosing x1 to be 6, for example. We'll get to that in a minute. Okay, so you choose this value here, and you evaluate the function at there, and of course it's not 0. It doesn't even look like it's that close to 0, relatively. And then you calculate the tangent line to the curve at that point, and you find where that line intersects the x-axis, and that's going to be your x2. Okay, and then you repeat the process. Okay, you find where that, and then you find where that intersects the x-axis, and that's your x3. Okay, and you repeat the process. And in practice, this is pretty good. It converges. Well, there's one drawback, but it in general, in practice, if you're close to the initial guess, if this guess is close to the initial one, then you're going to zero in on the zeros pretty quickly. It converges pretty quickly to the 0. Okay, that's usually what happens if you're close. But sometimes things can go wrong. So let me just give you the calculation. So let's take this one, right, this initial tangent right here. Okay, so the tangent curve right here, the tangent curve is, okay, so we're talking y equals mx plus v. We're talking that kind of stuff. Okay, so the equation is going to be f of x1 prime x, let's see here. Hold on a second. Okay, so the point is x1 comma f of x1. That's the point, right? So let me back up for a second. Let's use this form instead. So y minus the y coordinate equals the slope, which is this, times x minus the x coordinate. Okay, and the idea is you want to find out where this intersects where does it intersect? You want to find this x2 point right here, where it intersects the x-axis. So you're taking this equation of the line, and you want to find where it intersects the x-axis. Well, to do that, you set y equal to 0. So you set this one equal to 0. So you have 0 minus f of x1 equals f prime of x1 times, and then this is going to be your x2 minus x1. So right there. So basically, and then you set x equal to x2 in this equation right here, and then just solve for that. So let's see. This goes away, and so this comes over to the denominator, and that's negative there still. And then you just have x2 minus x1 over here. This one, this x1 will take, well, what's going on here? Oh no, we'll take this x2 over to the other side. No, we'll just solve for x2, okay? x2 is going to be x1. So you just take the x1 over here, minus f of x1 over f prime of x1, okay? And so this is how they come up with this equation right here. Okay, so x2 is x1 minus f of x1 over f prime of x1. That's a 1. Okay, so this is, oh, it's a really bad one. Make that better. That's an x1. Okay, so that's how they come up with that equation there. Okay, and then you do the same thing with x2. You run it through there. Okay, so some comments about this. So if you start with a point over here, then you're gonna converge to this 0 here. Okay, if you start with this point right here at the top, you have a horizontal tangent, then that's just gonna diverge. Okay, so if you start with this point, it's gonna diverge. You're not gonna converge to anything. So sometimes, you know, depending on what point you start at, if you start with the wrong point, then it's not gonna converge. But generally, in practice, usually when you start close to the 0, then it's going to converge to that 0. Okay. So let's look at this exercise here, number 1. The figure shows the graph of f. Suppose that Newton's method is used to approximate the s with initial approximation x1 equals 6. Okay, so 1, 2. So this is our initial approximation right here, 6, which you see the 0 is actually right here. Okay, so draw tangent lines that are used to find x1 and x2 and estimate the numerical values of x2 and x3. Okay, so what happens is you come down to here and you take the tangent line to the curve right there, and you see where it's going to come. So that right there is going to be x2. And it looks like maybe 7 might work. Let's see if 7 works. I wish this graph was a little bit bigger. I should have made it a little bit bigger. Okay, so 7 looks like it works. And then we'll say approximately 7. And then from there, we will use that one to come up to here to the graph right there, and then take the tangent curve there, and then maybe that point is 6.8 maybe, I don't know. Those are estimates. So, you know, if you do it yourself, then you might get something different, but that's the idea. So maybe a 7 should work here, and the 6.8 should work for this one. Okay, would x1 equals 8 be a better approximation? Okay, so if you started at 8, what would happen? Let's see here. So x1 equals 8. So if you started at 8, that's over here, right? And so then you come up to the curve, and that looks like it puts it closer. Yes, I would say it would be a better approximation because the tangent line intersects the x-axis closer to s than there's a first approximation x1 equals 6. Okay. Number 2, for each initial approximation, determine graphically what happens if Newton's methods are used for the function whose graph is shown. Okay, so here we're trying to figure out 2 roots, which are 2 and 6. Okay, if you start at 0, you start right here. That's right there. So what's going to happen? When you take the tangent line, that's going to put you to here. So x2 is going to be right there. And then you'll take the tangent line here, and then that's going to put you further out over here. And then that's going to put you further out. So it's not going to hit, it's not even going to ever come back to one of these. It's not ever going to come back to either the 2 or the 6. So then this would fail. Okay, so that it failed that time. It would fail. Okay, so x1 equals 1, and that's right here. Okay, this is the horizontal tangent. That's going to fail because it's not going to intersect the. Doesn't look like it intersects the x-axis anywhere. x1 equals 3. Okay, so let's see here, 3. So that's this point here. So that's going to, and you take the tangent, it's going to come down to there, and that's going to come up. That's going to kick you pretty close. So this one will succeed. It's going to keep getting closer. Okay, x1 equals 4. What happens if you put a 4 in? Okay, so here, oh, that's going to be a horizontal tangent again, so that's going to fail. And then, last one, number 5. So this is right here. It looks like that's going to get you there, and then that's going to be pretty close. So that looks like it'll succeed. Okay, so those are the answers to that. Okay, now let's do some problems where we actually use Newton's method.
For C of problem 2, it actually says the right answer is that it fails for x1 equals 3.
This fails?
Yeah.
Interesting. Okay, let me think. Let me rethink that. Okay, I guess I drew it wrong. Okay, so probably, dang, I can't erase it. So probably what happens is at 3, it's probably going to kick you out over here. Okay, that's probably why I messed up. I thought it would kick it in between 1 and 2. If the intercept's right there, then what happens is then it's gonna put you over here and fail. So we'll go with fails. All of them fail except for the last one. This is like, that's weird. All of them fail except for the last one. That's kind of a weird answer, you know? It doesn't give you a good impression of what Newton's method does. So I think that's probably what happened. Okay, so sorry about that.
That's all right.
Okay, number 3. We're going to actually use Newton's method. Okay, so here's our initial approximation, and we want to use that initial approximation to find x3. Okay, so here's the formula. I guess I should have put that down there. It's xn minus f of xn over f prime of xn. Okay, so let's go ahead. Here's f of x. It's 2x to the minus 1 minus x squared plus 1. And we'll find the derivative, which is negative 2x to the negative 2 minus 2x as the derivative, because that's the function and its derivative. So x2 is going to be, so using this right here, so we put in x1s here and here. We have 2, x1 is 2, minus this function right here, evaluated at, let me do this. This is 2 over x minus x squared plus 1. This one is negative 2 over x squared minus 2x. Okay, so it's 2 over 2. So I'm replacing everything here with 2's. Here, let me do this. Oh. So it's this f of 2 over f prime of 2, just to be clear. Okay, so that's 2 minus, putting 2's in here, That's 1 minus 4 plus 1. And this one is, dang, negative 1/2 minus 4. It's negative 2. This is negative 4 is 8 halves, negative 8 halves, negative 9 halves. Okay, so I get 14 over 9. I hope that's the correct answer for x2. And then x3, because they want us to find x3, right? So that's going to be x2, which is 14/9 minus f of 14/9 over f prime of 14/9. I'm kind of suspicious here. Is that really it? Dang. Okay, so numerator would be 2 over x, so that would be 2 times 9 over 14. So I'll just take the reciprocal, minus 14/9 squared plus 1 over negative 2 times 9/14 squared minus 2 times 14 over 9. I get approximately 1.5215. That's rounded off to 4 decimal places. Okay. Okay, so let's go to the number 4. Use Newton's method to approximate the 4th root of 73 to 8 decimal places. Okay, so you want to approximate this to 8 decimal places. Actually, okay, let me show you a better way to do this. Okay, so because they can't be doing this by hand. This is just too much work to do by hand. Okay, so but let me show the number 4. Okay, so x, so let's let x be the 4th root of 73. Okay, so the idea is you want to come up with an equation where this is the solution, or one of the solutions at least. And so if you take both sides to the 4th power, you get x to the 4th is 73, and then you take the 73 over the side, so you have equal to 0. Okay, so Newton's method is for finding zeros of functions, and so then we let our function be x to the 4th minus 73. Let that be our function. Okay. So let me show you a better way to do this problem right here. So remember that this is our, so let me do this problem right here using Excel, okay? So remember that this is our original function, this is our derivative, and then we'll do this problem, okay? We'll come back and do that one. Okay. Okay, so I've set up an Excel spreadsheet here. and this is number 3. I got that set up. Okay, so our initial value was 2. So I'm going to put a 2 there. Okay, they said start with initial value of 2, and then xn plus 1. Now I'm going to put in the formula. Okay, so I'm going to say equals. That means it's going to put a value there, and then I'm going to go B3, which is going to give me, we kick that one back, it's going to give you the 2. It's going to put the 2 in there, or going to put whatever is in the B3 cell, which is 2 right now, which is x2. Okay, and then minus, and then for the numerator, I have 2 over x, or 2 over b2, minus x squared, which is b2 squared, plus 1. Okay, and then that's the numerator, that's f of x. The denominator is f prime of x2. Okay, so that's going to be, the derivative was negative 2 over b2 squared minus 2 times b2, minus 2x, times 2x2. Okay. And what? That's weird. Oh, why did, oh, B3. Okay, so B3, you got to get that right. Okay, so that's 1.56. Okay, now here, I'm going to make this cell equal to C3. Right there. And then I just drag that down. Okay, and then that's where you can get your, that's going to be the answer right there. This 1.5215. 1.5215. Okay, so that will be the answer to that one. Let me see. How can I highlight that cell? Forgot. That's weird. There, that's the answer right there. Okay. Okay, and then also, if you want to go further, then if you want to continue doing Newton's method, this is what happens if you continue doing using Newton's method. Okay. So now, but this one is the answer right here. Okay. So now let's go back and do the next problem. Okay, so this right here. So here's our f right here, and our f prime is going to be 4x cubed. Okay. So x n plus 1 is equal to, here's the formula. So it'll be, the numerator will be x n to the 4th minus 73 over the derivative, which is 4 x n to the 3rd. Okay, so I'm going to put that information into Excel. Let me go over and put that in there. This is number 4. Right. So now the cell is B18. So that's equal to xn, which is B18, minus, in the numerator, it's going to be f of xn, which will be B18 to the 4th minus 73. And in the denominator, it's going to be f prime of bn, which is going to be 4 times B18 to the 3rd power. That'll be the denominator. Of course, it's like messed up now. So what we can do is we can like start with any value that you want. We'll start with 1. If we start with 1, then that's going to give us 19. Okay, now this column right here, we're going to make that equal to C18. Okay, and then we'll drag that down and drag this down. Okay, now that doesn't seem to converge. But remember, what we're after right now is the 4 through to 73. So it's not going to be 1. So let's choose something that's closer as our initial value. Maybe 3. So let's see here. 3. Yeah, that probably would be closer. 3 would probably be closer. So if we start with a 3, then that converges pretty quickly. The problem said for us to get it within 8 decimal places, and so you just look at these values here, and we're already right there. It's within already all the answers here. All these answers are the same. It's giving you back the same thing. So when it gives you back the same thing, that means that that's probably the 0 right there. Or you're really close to it. I mean, or that's probably it compared to how many decimal places this is. Okay, so the answer can be 2.9230127.9. So around that second to last 8, round that up to a 9, and that's going to be your answer. So let me go back. And just write some notes here. So see Excel. See Excel document, and 2.9230127, no, round that 7 to an 8. Oops, what the heck? Yeah. This is the worst. Okay, so the 4th root of 73 is approximately 2.9230128. What the? Huh, oh well. Okay. So let's go to the next one. Consider this function right here on the interval from 2 to 3. Okay, so part A, explain how we know that the given equation must have a solution in the given interval. Okay, so here we have, here's the polynomial right here. Let f of x be this left-hand side. And the polynomial f is continuous on 2 to 3. All polynomials are continuous everywhere. F of 2, so if you plug a 2 into here, then you're going to get negative 11. And f of 3, plug 3's in for x, you get 32. Okay. So that means that, so here, let me just drop a picture here. So if that's 2 and that's 3, then f of 2 is negative 11, so f of 2 is down here. F of 3 is 32, so f of 3 is over here. Okay, so that means, since this is negative, that's positive, that means that somewhere in this interval, it's got to cross through the x-axis, which will be a solution to this. Okay, so by intermediate, that's the intermediate value theorem. There's a number c such that f of c is equal to 0. So it has to cross through this axis here. In other words, the equation has a solution. Okay, then part B is to use Newton's method to approximate the solution correct to 6 decimal places. Okay, so we're going to calculate the derivative. That's going to be, bring the 4 down, that's 12 x cubed minus 24 x squared. That's the derivative right there. Okay. And so we'll go back over and we'll just do this in Excel. Let me write the stuff down though. Okay, so x n plus 1 is going to be xn minus, okay, and the numerator is going to be f of xn, so it'll be this one right here, 3 xn, put parentheses, minus 8xn cubed plus 5. The denominator will be this one, 12xn cubed minus 24xn squared. Okay, so the Excel, and so we'll go to the Excel to finish this off. Okay, so what I've done is here I have B32, which is our xn, minus 3xn to the fourth minus 8. That's our f. So right up here is our f. Minus 8xn to the third plus 5. That's our f polynomial. And then divided by its derivative, which is 12xn to the third minus 24xn to the squared. Okay, now I put these weird numbers, but in reality, what you want to do is you want to choose some number between 2 and 3. So maybe 2.5. And you can see that when you choose an initial value right here, then it's going to converge to this right here. So this will be the answer. Okay. So 2.568, 284. Okay. So 2.568, 284 from Excel. Okay, and then that's just putting that in. Okay, now number 6. Use Newton's method to find all solutions of this equation right here. Correct to 6 decimal places. Okay, so what I'm going to do, now here's the trick right here. It's all solutions. It's not just like, oh, so there could be more than one solution, and we have to use Newton's method to find every single one of those solutions. So that can be challenging. Okay, so what I'm going to do is I'm going to do a rough sketch. I'm going to make this part will be in red. So 5 cosine x. So I'm going to graph y equals 5 cosine x. Okay, so it starts up here at 5, and then it comes down at 0. It comes down at pi over 2. It's going to be 0. So it comes down here like that, and then runs like that. Okay, and then meanwhile it comes over here like that, and then over like that. Okay, so that gives you an idea. Okay, now I'm going to graph this one, y equals x plus 1, and that is a line with slope 1. So that's going to go like that. So here's an intersection point. Oh, wait a second. I think okay, hold on a second. I have to be careful here. So pi is about 3.1. So pi over 2 is about 1.5 something. Okay, so I'm kind of distorted on this. So that means that I should draw this with not such a steep slope, maybe like that. Okay. So it appears that I've got 3 different intersection points, maybe a 4th over here. Although I doubt it because, yeah, no, I think I'm not going to be another one because this is going to be, this is like negative 1.5. This is going to be negative 3.14. This is negative pi, right? And then over here we even smaller. And then before it goes under again, this is going to be really, this green line is going to be completely below it. So it looks like there's a possibility of 3 of these. And then by the time it comes up here, this green line's above it because we're talking 3 something here. And then, which is going to put us at 4 something. And then over here, it's going to be what, 4.5, 4.6 or something like that. So it's going to be well above by the time it crosses over here. Okay, so we're looking at 3 intersection points. And what you're going to do is you're going to take this equation, and now we'll bring everything over to the left-hand side. Okay, because Newton's method, in order for it to work, you have to be solving for a function that's equal to 0, finding where a function is 0. Okay, so our function will be 5 cosine x minus 1. Okay, so that means our derivative is going to be negative 5 sine x minus 1. Okay, and then x n plus 1 will be xn minus, and then the numerator, we're going to have f, which is 5 cosine of xn minus xn minus 1. And in the denominator, we're going to have this one, negative 5 sine of xn minus 1. Okay, so in Excel, this is going to appear as some B cell, so B something minus, not XX. So B something minus 5 cosine and parentheses. So in Excel, it's going to appear like this. Let me undo the whole thing. Times cosine of B star star. Maybe not star star. Let me use number. Minus B number, because I'm in the B column, minus 1, and that's all divided by negative 5 times sine of B number minus 1. Yeah, so it's going to be like that in Excel, okay? Now remember, we have 3 different solutions to try to find, and just for let me do this. So before we go to Excel, let's try initial guesses, and then see if those work. Okay. So this is about 1.5 right here. This is and 1.5 and 0. So I'm going to choose maybe 1.3 for the first guess. Okay. So this one, we're going to choose 1.3. And then for the second one, this looks like a little bit less than 1.5, so negative 1.5, so maybe negative 1.6. And for the third one, maybe if we choose, this looks like it might be over here, might not be. Let's try negative 3.2. Okay. And we might have to adjust, depending on how things are going. And there might only be one. I think it's going to intersect in 2 places, actually. I'm confident that that'll do that. So let's choose those 3 values and see what values it gives us. Okay, so we'll come over here to Excel. And here, number 6, I've already inputted everything. So as you can see, here's the up here, we have the formula B number minus 5 times cosine of B number minus B, and so on. Okay, that's just the from Newton's method formula. So the important thing is, and then right here, this one is equal to C46, and then this one will be C47, and so on. Okay. So now our initial guess is we decided 1.3 to be initial guess. That looks like it converges to 1.1306. No, wait. Let's come down here. Okay, 1.130597. That's what that one's going to be. Now go back. The second one we decided on was negative 1.6. Okay, and that one, it looks like that converges as well. So maybe negative 1.714108. And then the third one that we decided on was negative 3.2. To try that one. And great, that one converges to a fourth number, so that's great. So negative 4.055053. So this third of the last two rounds up to a 3. Okay, so great. That gives us all 3 values. So I'll go ahead and save that. Come back and summarize everything. Okay, so choosing that value gave us 1.130597. Choosing this value gave us negative 1.714108. And choosing that third value gave us negative 4.055053. Okay, so those are the 3 values. So put those in with the commas in between, and that